Hello students, as discussed in the last module, in this module we will be describing the detectors, interception detectors in detail. We will start with the radiometers, which is a wideband interception detector. The radiometer, which is idealized wideband detector, its figure, if you see in the next slide, it is there. The structure of this detector is something like this. It takes the interception, it takes the incoming signal, it senses the incoming signal. The signal passes through an ideal band pass filter. Remember, the band pass filter bandwidth W will be almost matched with the signal, but it is not a matched filter kind of. And the output of this band pass filter will be passed to a square law detector, and the output of this detector will be integrated over the time duration of the t, and output of this integrator you are comparing with a predefined threshold th, and the estimation of this threshold will be done when the signal is not present. So, threshold is chosen with respect to the noise variance. In presence of the noise, we estimate some value of the threshold, and hence if the detected signal, here the square law outputs and the integrated signal is above that noise level threshold, we declare that there is a detection of the energy. So, that is the classical radiometer, the way it works. So, the signal plus the noise that it enters at the front end, that I have already discussed, and it passes through a band pass filter, that then it will be passing through a square law detector output, and it will be integrated for t seconds, compared finally with a threshold. And as I have also told you that this radiometer can give you an optimal structure for detecting any signal if the signal is having a Gaussian random, it is a Gaussian random process, and if it is having it is immersed or it is superimposed over a wide Gaussian noise background. So, under the Gaussian assumption itself, this radiometer can give you an optimal structure for detecting a signal. And also remember, when this Gaussian random process assumption is going on, in this the power spectral density of the signal will be small compared to the thermal noise. That is the another assumption underlying behind this detection process. So, this optimum radiometer, it has a band pass filter that is matched to the signal bandwidth. So, that is filter bandwidth, this filter is having the bandwidth of also W, and it will be matching with the signal bandwidth, as I have also mentioned. Remember that it does not have, as I told it, radiometer does not have any matched filter at the input, because it is assumed that the signal will be detected is unknown to the detector, right. So, you cannot have any unknowns, you cannot actually have any prediction on the spectral shape of the signal. So, this input filter, the input band pass filter, it is assumed to have an ideal band pass filter for our study right now, and suppose that it is having a positive frequency bandwidth of this W hertz, and by intent it will be equal to the signal bandwidth almost. And in reality, if a multipole filter is utilized, then the ideal filter assumption, it provides a simplification in this analysis. The output of this filter, we feed it to a square law detector, and that feeds to a t second integrator, and basically this square law detector and the integrator, basically it is a integrate and dump radiometer also we talk about, or we call it. And remember, in this analysis it will be assumed that the signal exists for the whole t seconds over which the detection is going ahead. These assumptions, so we have done in the last slide, it is the best possible performance one can hope for, since in the reality the timing will not be known in advance, and even the bandwidth also won't be known in advance in that situation. And the threshold detector, when it compares the integrator output with a known threshold or predefined threshold value, as I have told that that threshold selection is done in absence of the signal. It is basically on the noise. So, the received signal, let us see the mathematical form of the whole detector. We have a received signal at the input of the detector, which is having a signal as well as the noise part. If I see the first two components of this right hand side of the equation 1.4, they talk about your signal, and remember that we consider they are the in phase as well as the quadrature phase component of the signal, and they are having the equal signal energy of E. And the third and fourth terms, they are the band limited white Gaussian receiver noise process, and one is the in phase as well as the quadrature phase of the components, and they have the one sided power spectral density. It has a one sided power spectral density given by eta 0 by 2. We also assume that all the power of these signals is passed to this ideal band pass filter. Now, given that Yt is received, then we are interested in two terms. What is the detection probability of the detector? What is the false alarm probability of the detector? The false alarm probability of the detector will be given by this equation 1.5, and the detection probability will be given by 1.6. Remember very importantly that both the probabilities depend on basically three major factors. One is actually the capital M, which is equal to your bandwidth time product W into T. W was the bandwidth of the filter, band pass filter, and T was the integration time. So, W into T is basically the band time bandwidth product. So, M is equal to this W into T, and it is actually then the term that comes is equal to capital R. This capital R is basically the signal to noise ratio. Third important term is the del. Del is nothing but the normalized threshold value. We understood that we had a predetermined threshold value of Th, and if I am normalizing it with respect to the noise variance sigma square, which is at the output of the band pass filter. So, I will get the value of this del. And remember this 1.5 we call that it is this distribution is a central chi-square distribution with 2m degrees of freedom. This integrand inside is actually a central non-central chi-square distribution. This is a central chi-square distribution, and this one is a non-central chi-square distribution of same degree of freedom of 2m. So, we will be always concentrating on these two parameters when we will be talking in the corresponding slides. The detection probability PD also can be expressed in terms of the mark Q function, and it is shown in the equation 1.7, where your Q function will be basically can be expanded like 1.8. And now we are also important it is also important to know another factor related to the detector design, which is the false alarm rate. It is not only the probability of the false alarm, it is a false alarm rate, which is given by the probability of the false alarm divided by the total duration of this observation window capital T, or the time period of the decision. And so, apart from the PD and PFA, so false alarm rate is another important parameter and of our interest. Now, remember one thing, as I have mentioned earlier, if you know the three parameters in this equation, one is your capital M, second is capital R, and third is the del. Do you remember what are they? Del was the normalized threshold, capital R was the signal to noise ratio, and capital M was the time bandwidth product. If you know these three parameters, we can actually calculate the two probabilities PD and PFA. And there are several limitations related to this calculation of this radiometer parameters, but let us go ahead with the Gaussian approximation a little bit more. And we understand that these three parameters are sufficient to define your PD and PFA. When the parameter capital M becomes very large, the output density function will tend to be a Gaussian random variables going by the law, and hence the detection probability will be given by equation 1.10. It is becoming a Q function itself, and where the probability of false alarm also is becoming a Q function of a quantity beta, where this beta is basically a function of your threshold you have chosen, the noise power spectral density and the gain bandwidth product. And remember, this SNR, what we are writing here is can be given as P by N0 W, where P is the signal power and this is the noise power correspondingly. A Q function, we understand that is a classical formula that by which it will be given, and also this all the reasonable approximation holds good if the signal power is well behaved, including the kind of the modulation schemes of MFSK, MSK and the QPSK. And this Gaussian probability calculation, it is in the normalized form, is very simple to use. And if I am having choosing a false alarm probability, we can get a value of the beta easily, and once you get the value of the beta, which allows us the evaluation of the detection probability first, and then you can calculate the signal to noise if your SNR is known to that. So what I am saying is, in the calculation itself, if you go back and check, the Gaussian probability is involved. So if I go back and check the earlier two equations of PD and PFA after Gaussian assumptions, we will see that if I know the false alarm probability, given the false alarm probability, I can easily calculate the value of beta, and if I know the value of the beta, then I can evaluate the detection probability if my signal to noise ratio is known. So given my probability of false alarm and SNR, both the PFA, both the beta as well as the PD. So PD calculation can be done easily using the Gaussian assumption. Alternatively, suppose you know the detection probability itself, then the argument of this Q, of this detection probability, then this whole argument you can calculate, and if your detection probability is known and you are knowing having this guy, and then you can actually also calculate the SNR also if beta is given. So vice versa, means either you know SNR, you compute the detection probability, or you know the detection probability and the beta values, you compute the SNR. It should be also noted that the radiometer is having a we consider that it is having a negligible filtering loss. So that filter loss is not considered in the signal to noise ratio computation, but if there is a reasonable loss which is given by the alpha, it is a filtering loss, then the SNR should be modified by alpha into P by N0 W. And if I consider that this SF is a one sided signal power spectral density which is centered at the transmission frequency F0, then this alpha P, the signal power, can be integrated, can be obtained by this integration of over the bandwidth of capital B. So under the constraint that the pulse energy and the probability of false alarm, they are fixed, the pulse type that will help you to maximize the probability of detection, which is your main interesting part from the transmitter's point of view, will be sending the very low power and long duration pulse, but not the high power and the short pulses. So if the communicator originally is transmitting low power and very long duration pulse, detection probability for the inceptor detectors will be really very high. That's why actually in the spectrum communication we prefer to go ahead with the short duration pulse. High power sometimes we implement but we never to go ahead with a long duration pulses, because your detection probability increases. Detection probability by the interceptor detectors increases. The conclusion that we have made here, it is based on the assumption that the radiometer has a very large W into T product, and also we assume that the radiometer is perfectly synchronized with the pulse signal and the pulse energy. Pulse signal and the energy of the pulse is also held constant. So under all this consideration itself, the detection probability can go very high if I am introducing a short pulse, if I am going ahead with a low power but long duration pulse. Here is a good example to give you an idea. So, if I am trying to determine the synchronous or integration time that needs to be fixed in the detector design, such that to detect a signal which has a power level of minus 160 dB watt to a omnidirectional antenna, assuming that the Gaussian approximation is adequate, and if we are having the other information about the noise level equal to minus 200 dB watt per hertz, bandwidth of the signal is equal to 10 megahertz, and we wish to have a detection probability of 0.95, where the false alarm probability is equal to 10 to the power minus 2. So, how to proceed? If we take the values, if we substitute the given values in the equation 1.10 and 1.11, we will be seeing that the value is coming 1.575 seconds, and the corresponding value of the beta is coming 2.32 kind of. The actual threshold, this TH, it can be now found from this 1.12 also. So, given the probability of false alarm and the detection probability, if we fix both of them, and we have the knowledge of the signal bandwidth and the signal power to be detected, we can basically find out the value of the threshold for the detector, and also we can find out the integration time capital T inside the detector. So, if once we know the W, the bandwidth needs to be designed for the band pass filter of the detector architecture, time period for the integration, noise power spectral density, and also the value of the beta, the TH can be easily calculated. But there are several limitations of this wideband radiometer performance. First of all, it is heavily sensitive to the background temperature variation interfering signals. So, first is the temperature variation, second is the interfering signals that limits the performance of the radiometer. Why is it so now? Because the threshold that we fix for the radiometer, that is derived from the receiver noise process when the signal is absent, and hence the noise is the main part who is controlling the performance of the radiometer, because it is detecting, it is governing the selection of the TH. So, then threshold is not at all, it follows that the threshold is a statistical quantity, it is not a deterministic one, and always it is having some variation on the top of it selected values, and it again its statistical quality and it is a statistical property largely depends on the fact whether the input is only noise based on which you are selecting the TH, or input is a combination of the thermal noise as well as the other interfering signals that are present. And if I can actually improve it, I mean I can stabilize that value of TH by heavily filtering the threshold estimator. But if I do it, the heavily filtration, if I do, it cannot respond to the noise temperature variation. So, otherwise actually then again the detection possibility and the detection output will again fall. This is one point. Second point is, on the other hand, if I the threshold estimator filter is not very much narrow band, if I keep it wide band, then it will also have some larger output variations on it, because large number of the variations of the inputs you are taking to make your decision of the threshold selection. So, it can also change the detection and the false alarm probability dramatically. This is from the filter design aspect. So, some other aspects are there. The other problem is coming from the antenna background. Antenna background temperature, that is in the tactical environment, it depends upon so many factors. Number one is the elevation angle, second is the azimuth angle of the antenna, temporal variation, location of the detector. So, based on all that, the antenna background temperature depends on. So, when this temperature depends on so many factors and any one of those or the combination of those are varying, it affects the temperature, and once the temperature is varying in the threshold setting, of the received signal or the sensed noise value, it is varying, and hence actually the corresponding threshold setting will be varying. It will be also, you can note that this background interference, when we were talking about in the last slide, that input, when we are choosing the threshold, the input signal, we are thinking that noise is coming, but sometimes noise clubbed with some other interfering signals may also come into picture, and those interfering signals can come from the television, radio relay links, microwave links, multipath, and so on. So, lot of the sources are having, and each of these sources are having their independent kind of the profile of the interfering signals. So, it is really very hard to select the threshold for the radiometer, and as the detector output is heavily dependent on that. So, radiometer is having this typical sensitivity issues to the threshold variation. Performance is very much sensitive to the threshold variation. In these slides, in the next few slides, we will try to quantify the amount of the sensitivity of the radiometer threshold variation. We have already seen these two equations that we have derived in terms of the detection probability and the false alarm probability with a Gaussian assumption. And we can actually, if I combine these two, then detection probability can be also expressed in terms of the false alarm probability, where I have just replaced the value beta from the equation 1.11 in 1.10. And we understand that inside this SNR is given by the P into N0W classically without considering the loss of the filter, and P is the signal power, N0 will be the one sided noise power spectral density, B is the bandwidth of the positive frequency band noise bandwidth. So, 1.17 we will continue with, it is rewritten here, and if I solve the equation of 1.17 and try to find out what will be the expression for SNR, it will boil down to equation 1.12, and inside we have introduced new parameters called capital A and B. A will be the inverse Q function of this detection probability, and B is the inverse Q function of the false alarm probability. So, signal to noise ratio will be definitely a part of the false alarm probability of the false alarm probability and the detection probability. In terms of that, you can write down. And now we will try to see and get an assumption of how SNR is varying over the different components that are involved in this expression itself. One important part that I am seeing in this equation 1.18 is the quantity W into T, which is the gain bandwidth product. So, when this W into T is very large, so this equation SNR equation can be approximated on by equation 1.20. Here you see it is the difference between the false alarm inverse of the inverse Q function of this false alarm probability to the inverse Q function of this detection probability given by the square root of this gain bandwidth product. And so, one can compute the required SNR knowing the fact whether WT is large or WT is not that much large. If WT is large, then equation 1.20 will be implied, and if it is not, then equation 1.18 will be implied, but you will be in need of the expression, have knowledge of detection probability and false alarm probability. And hence, so once these two are done, so we can go ahead with the false alarm probability and the beta values once again, and from the either for the large condition as well as for the minimal condition. We also understand that the false alarm probability is given by the Q function of beta, where beta we saw that this is the expression for the beta in the last few slides. Now, from this expression of the false alarm probability and this one also, the ideal interceptor threshold value I can compute. Okay, this is the ideal, that is why we have given the corresponding false alarm probability as PF is 0 and the threshold is written as TH0. So, this is the expression when the ideal interceptor threshold will be given. Next, if the interceptor actual threshold now we wish to see, that will be an estimated value. That estimated value following the equation, previous equation of TH0. Similarly, the estimated value will be given by TH0 estimate. N0 will be also estimate, where N0 is the estimate of the one sided noise power spectral density. And now, since the threshold must be determined from the input noise process, and it will be proportional to N0 also at the output of the detector. The estimate can be close to perfection, but it will never be exactly the estimate of TH0. So, it can be, if it is not well perfect, it can be modeled by N0 hat, and there will be it will be assumed to satisfy the constraint. So, N0 hat, which is controlling the estimate of TH0 hat, in when the estimation is not well perfect, this estimate of N0 hat will be actually given by these two constraints, where this value of the epsilon 1 and epsilon 2 is chosen such that the epsilon 1 should be varying between 0 and 1, and epsilon 2 will be greater than or equal to 0. Now, we will see actually the effect of both the sections, left side and right side of this equation, in the following discussion. And this N0 estimate, now I can actually replace by means of the threshold estimate to the given threshold, actual threshold or idealized threshold. It is a ratio of these two. Actually, this estimate hat, TH estimate hat, will be exactly with the value of TH0, when estimate of this N0 will be equal to the actual value of N0. Now, remember one thing, if the threshold estimate satisfies, this threshold estimate satisfies is coming equal to the left part of the value, then the observed false alarm probability will be greater than the desired value. It is the meaning of the case. And if it is greater than if the false alarm probability will be greater than the desired value in the ideal situation, and hence it will be increased, should be increased by a factor of 1 by 1 minus epsilon 1 to obtain the correct false alarm probability. On the other hand, if the noise level satisfies the right hand side of the value with the equality, then it must be increased by a factor of 1 plus epsilon 2 to ensure the achievement of this desired false alarm probability. So, this is the meaning of your estimate and choice of the proper threshold with the false alarm probability basically. So, either in one case it is increasing and one other case it is decreasing. So, anyway actually the estimated false alarm probability will needs to be readjusted based on actually where your estimate lies between. So, it is concluded that the worst case threshold must satisfy the relationship of 1.26. Your threshold is worst chosen. So, you have it will be our factor of this actual threshold values. This u we call it a peak to peak uncertainty involved, which will be given by this factor of 1 plus epsilon 2 by 1 minus epsilon 1. If we define that the signal to noise ratio needed to achieve detection probability which is greater than the actual detection probability, or false alarm probability which is less than the ideal false alarm probability over the entire range of uncertainty of this u, then using this 1.26 and using this equation, earlier equation we have seen for the ideal threshold selection, and the detection probability of we can get actually the detection probability substituting the values there in the detection probability in terms of u into th, simply replacing the th with u into th with the worst case probability. We can now get a new expression for this signal to noise ratio in terms of this uncertainty of the peak to peak uncertainty. So, we have now updated the equation of the SNR in terms of the uncertainty. And now, if I put this uncertainty value equal to 1 in this new SNR expression, you will get back the original, the old expression that we saw when we replaced the detection probability in terms of the frequency of false alarm probability itself. And when my WT in this equation and also in 1.29, when this WT becomes very high, greater than 1, then SNR can be easily approximated only by the uncertainty factors and the factor of A. It is simplified actually. And for very large value of the WT, the minimum value of this SNR that is required, that satisfies, so value of the SNR satisfies actually u minus 1. So, what exactly we are getting at last is the parameter SNR mean. It is the minimum value of the SNR which is needed, it is basically needed to overcome the threshold level uncertainty irrespective of the detector parameters. I mean, whatever be the value of PD and PFA and the integration time you are involving in the detection process, this is the minimum value of the SNR you should ensure, so that the effect of the uncertainty on the threshold selection can be avoided. Okay. So, that is all about your threshold, that is all about your radiometer performance analysis and the radiometer's selection of the SNRs and its sensitivity issues. And we could realize that the radiometer is not a implementable solution because of its effect of the uncertainty effect that is there in the threshold selection itself, and the sensitivity issue is really very crucial for the practical applications, where the message duration will be also very small, and once actually the threshold itself is not certain, and detection probability cannot be ensured to that level. So, in the coming in the next module, we will try to look into whether we can have some realizable solution for this intercepting detector architecture or not.